Okay.
Okay, so let's welcome Joaquin Berenguer with a talk about Internet of Things.
Yeah. Thank you very much. Good afternoon. I hope you like the presentation. We are going to talk, as he said, from Internet of Things that gives you a better idea of what's going on there. Okay. We are in front of some big business in front of us. As you could see here, by 2020, more than 25 million apps is going to be there. Well, it's difficult to have in 4 years so many applications, but okay, that's what they said. But in case that's not true, what is going to be true is that the revenue opportunity there is huge. And the gigabytes of data that are going to be managed is going to be huge as well. As you could see here, the reports that all these sensors are going to send to be stored will be huge because the number of sensors around are going to be also huge. So new analytic engines are going to be needed because to reflect good feedback to the control again sensors send right information to the data stores. In order to go ahead with this, I have implemented something regarding a server that manages those kind of devices. We'll see the environment, the architecture, a certain functionality, some security that is needed, what type of IoT devices could be used here, what kind of access from mobile and desktop devices could be sent, and what are events, alarms, sensors, and actuators, and what I think about the future about this. The environment is Python 3.5.1. For the devices that are accessing the server is still not there, it's 3.4. But the server actually is based on threading and queues. They share nothing. They communicate each other using queues. The database being used is MySQL, and I have the MySQL connector comes from Oracle. And some personal libs that are going to be used as well for MySQL and for managing USB or general functions. And everything is running in Ubuntu 16. Okay, this is the architecture that is actually up and running. When any of these devices in this part are powered on, what they need to do is to register themselves into the server. So they send a message to the server, well, here I am, my name is that, or whatever. And if it is okay, if this right device registered in the MySQL database, then the IoT server adapts a new thread for this device. If not, the thread is terminated and is rejected the communication. So is what any of these devices, it doesn't matter where they are using Wi-Fi, is what they need to do. We will see later what type of devices are those. On the other hand, Kiwi, as is in the text that you have already in the schedule, or Flask application, which is better, are using Socket.io. That means we are going to, because we need a persistent connection, we are going to use Socket.io WebSockets, and any web browser that supports WebSockets is going to be valid. So any of these devices are going to connect also to the MySQL database using user and password. And when that's done, they are ready to send messages to any of these devices below. In order to have an idea of what's going on, we have here a small application that supports that. We have a small that. And then we have here online, we have extracted what kind of devices are connected to the server. We could use this one, and we could know all these kind of functions that really are now a possibility to have in those devices. We could say, okay, we want to know temperature, pressure, humidity on that device. We send back to the server and give us what kind of measurement this device is having it. So this is the way that's happening. So we have connect using your user and password. We have a persistent connection that will be valid for the rest of the presentation, and all these devices are ready to answer any message that we are going to send. As I have said, the front end is a Flask plus Socket.io. Messages to and from modules are executed using this Socket.io 1.4. And to send messages from the devices to the application, to the Flask application, we are using Socket.io client in Python, as we can see here. And how is this going? This is the part of the web browser. We define a number of messages for connection, for example, and this JavaScript is sent, and at the end of the day, what we are going to execute is a function in Python that receives the message, which is the message containing origin, destination, and what type of function we want to execute. And once it's in the environment of Python, okay, we execute everything what we want, just defining naming of the message and the namespace. Inside the server, what we have is that every time a server is waiting for connections from the IoT device, once one wants to be connected, what we start is a thread socket, a thread queue, and those are blocked waiting for a message. They are doing nothing. In the future, I think Async.io could be better. By the moment, is running on threads, taking into account that those threads are corresponding one customer, and every customer will have their own server. So this could be enough, but Async.io will try to make it happen as well. So the parameters to define a device at the end of the day is we need to know what kind of device, the ID of the device, the serial number, the server name, and the server port. With these 5 that are stored in each of the IoT devices, the first thing they are going to do is using server name and port, connect to the port of that server, and the server using type of device, ID, and serial number will know if there is a good IoT device to be connected. 3 types of devices are happening here. We are going to have MKR 1000 we see later that will use flash memory, or eMCC with Blackbone, or SD card with Raspberry. The serial number, by definition, never is sent through the network in order to have more security. We will see later how this is going to happen. And different servers, the only thing that have is connect, change the port, and we will have another server useful for other devices that are going to be connected. Actually, the server name is probably using this no IP. The message format always have 3 fields that are mandatory, which is origin, destination, and message type, as we have seen here in the application. The origin is this web browser, destination is this connected module, and the type of message that we want to send is this one. Okay, the rest of fields that depends on the message. We will add parameters on there that will have variable length, and we'll finish with EOT. Security is used using SHA-256. We are using haslib SHA-256 in Python, and in C implementation for MKR 1000, because need to be in C, we are using ATML documentation, and there is a SHA-256. And devices are grouped by customer. So only IoT devices from one customer could talk with those around. So inside the server, what we have is an origin thread that is sending to the key of the destination. From the key of the destination goes to the device. The device executes the function and come back with the results, who goes to the origin queue, and from there to the destination. We could again we are sending this from this origin to the destination. We want to have we could read the gyroscope of that device, and then it's accumulating here what's going on. But the system is always the same, using queues and thread and sending the message. So we are going to define two types of devices: low consumption, and we have here an example of device. This is the size of this device. It's nearly nothing. And this is the battery that we could attach to this. And with this, we could have it on your dress. And with that, you will have the possibility to do anything that you want, because you could connect this device to your phone as an access point, and from there goes the information to anywhere. So we have here Wi-Fi, and we have right. So with this, we have low consumption. 2-3 weeks we could have with this. We have a lipo cell. The Wi-Fi range that these devices have is more or less the same as a laptop. If one laptop arrives to 100 meters, this could be the same or more. You have here the calculations if you like to have more information. The Wi-Fi modes, the normal thing is this is a client, a station, but also could be used to have a range extension. These devices could be used as well as an access point, and that means that we could connect one with the other and extend the range, because we could resend the message to the following one. And these are the advanced modules that have been used. So all of them are Linux embedded. Most of them are Debian. And these we using here also a Python. Raspberry Pi is about 45. We could use OpenCV. In this case, it's more because the information or the documentation is not good enough, and the contract you could have with Raspberry is not all limited permissions you have there. Media and education is where we could apply it. PCDwin is good for, also has an Ubuntu inside, Ubuntu embedded board. We use 3.4 Python, and it's good for the ones who have already things done with Arduino. And for me, the favorite is this one, BeagleBone Green Wireless. It's about 44. There is a lot of documentation, Texas Instrument, CPU with Debian or Ubuntu is the one you want, and this is good for industrial environments and also commercial products, because you have any kind of protocols, communication. It's quite, this is this one here. The mobile and desktop devices, the only thing that is needed is that a web browser that supports WebSocket, because we need, as I have said, a persistent connection. We have that using Flask and Socket.io, and that's alarms and events. So we need alarms from the devices in order to send us directly messages if a temperature is above or below a number, but also we could schedule events that in our case will appear in the text area here below. If we use this event and we send this message, what usually should happen is that the device is sending us events that will appear here downstairs in this area. So anything, any several seconds in this demo, are going to be in this text area downstairs, but also are registered in the database. So we are producing information from every one of the devices that we have in front of us, and they are producing information that we're going to analyze or treat in any manner. If we send the same event again, we stop sending us more events. And that's the way how we generate alarms and events. Sensors, we have seen here any kind of sensors, it depends on you, which ones, because it's above any kind of application and sensors could be used. In the case of actuators, what we name an actuator is everything that we have a write from the device to the environment. As a matter of example, we could again go to the application and use, well, I have here also this camera that this is a Raspberry, you see, is about 5 or 6 centimeters by 6 centimeters. And we have here 64, let's say, LEDs or lamps or whatever, because the only thing we want to do is right there, we could write pixel. We say, okay, we want to write pixel number, I don't know, 26, and we send and here we have the color. We could say, okay, blue or whatever. And when we have sent this pixel, the pixel number, whatever we have set is on, we could send letters, or we could send messages as well. So any kind of possibilities are on top of what green or so this is what we could do with writing, and any kind of send a message that writes goes in that direction. In the future, again, software is the most important. Either C or Python extension of Python using C and many applications are going to develop around these. Products like Civilly or from Login, ThinkSpeak, or Azure from Microsoft are good examples of what's going on in this area. Hardware will continue to integrate more parts of the application, decreasing price and size. Wearables are there, and we have seen them. And the industry will take advantage as well of substituting the actual solutions that are in the market. Okay, that's all. Thank you.
Does anyone have any question? Okay, so if nobody has a question, then let's thank you again.
In GitHub, Joaquin.bb, you have documentation from here. Thank you and goodbye.
Okay, so welcome back. Let's find out if monkey punching is a magic trick or a powerful tool. Welcome, Elizaveta.
Hi, my name is Elizaveta Shashkova, and today I want to tell you about monkey punching in Python. In this talk, I'll try to give the answer to the question, is monkey punching just a magic trick, or is it a really powerful tool? Just a few words about me. I'm a software developer in the JetBrains company. I work in the PyCharm IDE, and I develop debugger in PyCharm, which is also used in PyDev, the Python IDE for Eclipse. Monkey punching is a dynamic modification of a class or a module at a runtime. Here is a simple example which illustrates what monkey punching is. The standard module math has a square root function, which returns the square root of a number. But if the number is negative, this function raises an exception. We want to change the behavior of this function. So, what can we do? We save the original square root function to the attribute original of the module math and replace the square root attribute with our new function, save square root function, which doesn't throw exception for negative numbers and returns the not a number constant, which is defined in math module. So, what happened here? We've got the standard module and changed its behavior inside our program. That means that monkey punching allows us to change third-party code without changing the source code, secretly. It explains where does the term monkey punching comes from. It believes that it has come from the term guerrilla punch. Guerrilla is a member of a group of soldiers who don't belong to a regular army and who fight in a war secretly. This term is referred to changing code secretly and possibly incompatibly with other such patches. It's believed that later this term was transformed to guerrilla patch, which sounds similar, and later it was transformed to monkey patch. As you might already notice, all these terms has another rather negative meaning. But despite of it, monkey punching exists in a number of other programming languages. For example, in Ruby, you can redefine any method in any class, including the standard modulus like string or array. In Ruby, it's named reopen the class. In this example, we replace the standard uppercase string module with the reverse method. As we can see, the monkey punching in Ruby is almost a part of the language philosophy, because there is even a special simple syntax for doing this. So, what about Python? I believe that everybody here remembers the Zen of Python and one of the most important statements in it. Explicit is better than implicit. Monkey punching doesn't satisfy this requirement because instead of raising explicitness, monkey punching makes Python code less readable and more difficult for understanding. And if in Ruby we can patch everything, in Python we can patch almost everything. Because on Python level we can't patch built-ins defined in C. There are some solutions for that case too, patching on C level, but we won't discuss them today. So, as you can see, monkey punching is a very interesting tool. It gives you a lot of opportunities and also imposes the great demand on the person who uses it. Now, let's have, like every object in our galaxy, monkey punching has its own light and dark sides. Now let's have a short survey. Please raise your hand if you're on the light side of monkey punching. Well, and now raise your hand if you're on the dark side of monkey punching. Okay, I would like to start from the light side of monkey punching and consider how we can use it in real life. So, as I've already mentioned, we can change the third-party code without changing the source code. And for example, if you found a bug in some library and you know how to fix it, you can just apply patch to this library and use the correct version of the library inside your program. But Remember that nowadays almost every library is open source, so the best decision is to fix this bug and create pull request and share your fix with other users. The next important example of usage of monkey patching is code instrumentation. You can use monkey patching in order to add performance measurements to your code without changing the code of your project. Also, sometimes tests need to invoke some functionality which depends on global settings or which invokes code which cannot be easily tested. A lot of test libraries allows you to replace parts of your system under test with mock objects. And the next important example is changing the standard modules. This point looks similar to the first one, but it's not about bug fixing. Sometimes there is need to change the standard libraries for your own purposes, and there are some libraries who do it. Later we'll consider such an example. It's time for examples. The first example will be from the PyCharm internals. As I've already mentioned, I developed debugger inside PyCharm. And it's very important for us to catch all the new processes created in the user's program in order to add debugger's tracing to these new processes. And monkey patching allows us to do it. Here we catch new processes created with the fork function from the module OS. We define a very simple class, process manager, which takes the original fork function and calls it in the method doFork, the patched version of this function. It calls the original fork function and checks the result. If result is 0, that means that we are situated in the child process. We call our debugger's tracing function, start tracing, and after return the process ID, like the original fork function does it. How can we use our process manager? It's very simple. We import module OS, create the instance of our project manager class and pass the original os.fork function to it, and after that we replace attribute fork of the module OS with our method doFork. And after that, every time when we call os.fork function, we adding our debugger tracing to every new process. The next example is about import hooks. Almost every script starts with the import statement. And every time we're importing some module, we in fact call built-in import function. Let's try to monkey patch it too. In the previous example, we patched the os.fork function, but what if we want to patch some module as soon as possible? As soon as possible means right after importing. That's why we need to create import hook. This is import hook manager class, and it's look very similar to the process manager class. It also saves the original import function and calls it inside the patched version of this function. But also it checks the name of the module, and if the name of the module is the string OS, that means we want to patch the object of our module. We again get the original attribute of the module, create the instance of our process manager, and replace the attribute fork of the module. And like standard import function does it, we return the object of the module. How can we use our import hook manager? It's very simple. We import built-ins, the module where is the import function situated, create the instance of import hook manager, and again replace the attribute import of this module with our new method. And now every time when we type import OS, it will be patched as soon as possible, right after importing. And the third example on the right side is related to the G-Event library. G-Event is a framework for scalable asynchronous input and output operations based on the green LED loop, a lightweight coroutine. It implements its own event loop, so even one-threaded programs are not blocked by the I/O operations. That's why G-Event library is very useful. But there are blocking system calls in the standard library, including, for example, socket. And when you use such modulus in your program, you break the main idea of the GMAT library, because your I/O operations becomes synchronous back. In this case, you can replace some statements like import socket with the modulus from the G-event library, which are very similar to the standard modulus, but which are compatible with it. So instead of import socket, you should just write from G-event import socket. But if you already have an application which uses such modulus, there is no need to modify such import statements in many places, because there is a special module inside G-event, gevent.monkey. It carefully replaces functions and classes in the standard modulus, and after that they can be used together with that library. It allows pure Python applications and libraries to become synchronous with no modifications. Monkey patching has many interesting and useful applications in real life, like changing third-party code, testing, code instrumentation. Monkey patching is a very powerful tool. But monkey patching is a very dangerous tool as well. As I've already mentioned in the beginning of my talk, monkey patching violates the philosophy of Python language. Changes made by monkey patching are not explicit. When you patch something, it leads to the unpredictable behavior of your program. Changes are not documented, and they may be very unexpected for people who uses your code. Also, even if you documented your monkey patching, sometimes you can meet people who decided to monkey patch something too, and it will be very sad to realize that you decided to monkey patch the same object. The examples on the dark side of the monkey patching are also very important. And this example will be related to the G-event library again. In this example, I want to show you how monkey patching can lead to creation rather complicated and tricky solutions. As I've already mentioned, the G-event can monkey patch some standard modulus in order to easily make Python applications asynchronous without a lot of change of code. In the docs, the creators of the G-event library mention that patching should be done as early as possible in the life cycle of the program. But what happens if user runs the program with G-event patching inside PyCharm's debugger? The debugger has its own event loop based on the standard modulus. And after G-event monkey patching, user's program is based on the G-event event loop. But two of these event loops should be separated, because debugger shouldn't affect user's event loop. It shouldn't break the logic of the user's program. So that means the debugger should use the original versions of modules, like threading, a suffix, or socket, instead of patched versions. So that means that we have a problem. Somehow, we should save the original versions of some standard modules and continue to use them simultaneously with the patched versions. Let's try to solve this problem. First, let's consider how the importing in Python works. This is a very simplified version of the standard import function. First of all, import function is trying to find the name of the module in the sys.modulus dictionary. This dictionary contains the objects of all imported modulus, and the keys of this in this dictionary are the names of these modulus, just strings. If the import function didn't find the name of the module in this dictionary, it executes the file again, creates the new object of the module, and put it to the sys.modulus dictionary and returns it as a result. Let's create some module saved modulus. Here we import socket module, so that means that after that it is situated in the sys.modulus dictionary, and the key socket is inside keys of this dictionary. After that, we pop the object with key socket from this dictionary. What does it mean? This object is not inside the dictionary, but we still have a link to it. And after that, when we import the socket module again, the import function is trying to find it inside sys.modulus dictionary. It can't find it, and it creates another object of this module and put it to the sys.modulus dictionary. And after that, we have two objects of our socket module, and one of them is situated in sys.modulus dictionary, and another of them is in our secret module. So, how can we use it in our program? We can import both, we can get access to both of these objects, but after that, when gEvent is trying to patch module socket, it is patching the module which is situated in the sys.modulus dictionary, and gEvent doesn't know anything about another module, but we know about it. So that means that we can use both of these modules, the patched version and the original one, together and simultaneously. So, as you can see, the solution of the problem was not very easy, because we tried to fix the bug after monkey patching, and we had to create some dirty hacks with importing. So, monkey patching can lead to some complicated bugs and to complicated fixes of them. Today, we considered both sides of monkey patching. Monkey patching has many different and interesting applications in real life, like changing third-party code, code instrumentation, testing, working with standard modules. But monkey patching raising the implicitness of the code. It can lead to some unpredictable behavior and surprising bugs in your program. Sometimes it may be incompatible with other such patches. I believe that sometimes you can use monkey patching in your program, but you should use it if and only if there are no other solutions for your problem. If and only if you're absolutely sure that it is necessary in your case. Monkey patching is a fascinating tool, but monkey patching is a very dangerous tool as well. As for me, I'm on the light side of monkey patching. We use it inside PyCharm because it's a really powerful tool. Be brave, but also be careful. Thank you.
Okay, so now I believe that we have some time for some questions. Does anybody of you have some?
I don't know if you're allowed to do this, but can you elaborate on some examples of how you use monkey patching in PyCharm?
Sorry, could you repeat your question?
Can you describe some instances where you use monkey patching in your work at PyCharm?
Yes, some of these examples were from the PyCharm internals. So the example where we catch new processes, we use it inside PyCharm's debugger, and the import hooks, we use them inside PyCharm too. And these solutions for to protect from monkey patching is used inside PyCharm. So, all of these examples.
Okay, any other questions?
Thank you for your talk. You mentioned at the beginning using monkey patching for testing.
Yes.
I've seen mocking, like the mock module and libraries. Is that, or do you use those, or do you use monkey patching directly? Because my worry is that if you monkey patch in a test, then surely the next test, or maybe I'm misunderstanding, will have that monkey patched object.
some testing libraries, they use monkey patching inside.
Internally in the library, but not in your own tests.
Yes, yes. Where
Okay.
I mentioned testing in the light side of monkey patching, I mean that how they use monkey patching in testing libraries.
Okay, great.
There is no need. Sometimes, of course, you can do it, but there is no need to do it on your own because there are a lot of powerful testing libraries,
Okay,
which
thank you.
who already does it for you.
Any other questions?
This may be a dumb question, but can we not solve the problem of monkey patching by not doing monkey patching, by creating new objects or classes that do the same thing with the monkey patch that we want to do?
So the question is, can we avoid monkey patching? Or what?
Yes, by creating new objects, so we will only use those instead of changing the ones that we want to change. So for example, in that example, the OS example, you create like monkey patch OS, and you use
Yes.
that instead of the OS, instead of changing OS.
Yes, we in this example we monkey patched the module OS, which was already imported, and we monkey patched the function inside it. So what?
Right. So my question is like, can you not create a new OS?
Yes, you can create OS, and in this case we should monkey patch it too.
Okay.
Oh.
Okay.
So there are some possibilities to avoid such monkey patching as which we did, but this example doesn't protect us from this from the solution which was shown in the example of the dark side. Yes. Thank you.
Okay, do you have any other questions? Okay, if no, then enjoy the coffee break, and let's thanks again, Elizaveta.
I'll just try something. He's with Fabio. Want a headset? I can give you the headset. Yeah, and I can tell you how to turn it on and off. So it's a bit different than the ones that I'm used to. Yeah. So yeah, you have to put it underneath. Yeah. So this is yeah. So maybe it's like this. These are your ears, and this goes. Yes, that looks good. Now, to understand how this turns on and off. Well, good thing we have two talk managers. So this one, either doesn't have batteries.
Hello everyone, our next speaker is John Sutherland and he's going to take us on a tour of iteration on Python. Please give him a big hand.
Thank you. Can you hear me okay? Okay, good. Oh. Good afternoon. Thanks for coming. I realize it's late on a Friday of a long week, so thanks for coming. So this is iteration. This is my name. Pretty good first slide, I think. This is my internet name, where you can find me on Twitter, GitHub, Telegram, and I'll be tweeting links to the slides afterwards. I work at a place called FanDuel in Edinburgh, Scotland, where we make an online daily fantasy sports thing, but I'm not going to be talking about that. As I already mentioned, this is iteration. So most of the programming is loops, conditionals, and a few other bits and pieces, and everything else is a kind of nice to have on top of those two things. So what we're going to cover this afternoon is, or what we're going to look at this afternoon is some basic loops, recursion, look at reduce, iterators, iter-tools, list comprehensions, generator expressions, generators, coroutines, and then at the very end, some stuff that you really shouldn't do.
Unplug and plug in again? Or?
Okay. So we're going to use a contrived example of factorial for the first few examples, just to demonstrate some of the basics. It's quite boring, but reasonably well understood, and hopefully you'll be able to see the differences between the different methods. So for anyone who's unsure or can't remember from their high school maths classes, 4 factorial, so 4 bang here is 4 times 3 times 2 times 1. So the while loop, so Python has while loops, which you don't see that often, unless you want to create infinite loops, which I do all the time for fun. And here's factorial with a while loop. So we can see here the iteration state, which is the variable n, the calculation, and the actual looping itself are all kind of bundled together in these 3 lines. There's quite a lot going on here, and you would never really write this, I don't think. Not like this anyway. This is Python, and we can do better. We have the for loop. So the for loop version of factorial is something like this. So we would iterate through a range from n to 1. So in this case, we're actually going backwards with the -1 on the end there. And every time we're going to multiply our accumulator fact by I, and then return that at the end. And this is nice. This is probably the best way to do this for this case. But the problem is our factorial logic and our iteration variable are all sort of hooked up together. So we could do it with a recursion. So some of you may have noticed that 4 factorial is actually 4 times 3 factorial. So the definition of factorial is recursive. And in the general case, n factorial is n times n minus 1 factorial. And we can see that quite nicely in this code. So here factorial, the definition of factorial includes a call to factorial, which is recursion. So the if here is our escape clause, and this prevents us from looping or recurring forever. For larger values of n as well, we could blow up the stack and we'll get a runtime error. So we should probably use the for loop version rather than this recursion. And the last of our factorial examples is with reduce. So what we're going to do with reduce is we're going to create the numbers 1 to 4, and then we're going to use the reduce function and the multiply operator to collapse our list of 1 to 4 or 1 to n into a single value. Since Python 3, reduce moved into functools, but previously it was a built-in. And this works. And this is reasonably clever, but where I work, and certainly if I was code reviewing, you'd be getting a thumbs down on that one, or a nice suggestion. Would you mind changing this to a for loop? So slightly more interesting than factorial are iterators. And iterators are created by calling iter on an iterable. And a lot of this was quite confusing and quite complicated, but hopefully we'll be able to follow it through. So iterables implement one of two protocols, the iteration protocol, which is the dunder iter method, or the sequence protocol, which is dunder get item, and we're passing in integers starting at 0. And then iterators, not iterables, iterators implement the iterator protocol, which is dunder next. So here we create the iterator of a list 235 into our iterator, and then we just successive calls to next yield the values 2, 3, 5. And if we call next on an exhausted iterator, then we get a stop iteration at the end. In practice, though, you would never actually need to catch that stop iteration because you would use this in a for loop. So this is a little bit more useful, or a little bit more common. Fibonacci, just to go full steam ahead with the trivial examples. Here it's an iterable because it implements dunder item, or dunder iter, sorry, and it's also an iterator because it implements dunder next. So iter tools. There's lots of cool things in iter tools, and you should have a look at them yourself. Just have a look in the docs. They're reasonably good. One of them is itertools.count, which just generates a forever sequence starting at 0, or the value that we pass in. So it's a little bit like range, but instead of a stop value, we just have a start value, and it will go on forever. We can also pass in a stop value and a step value as well. But this basically goes on forever. A couple of the other ones in there, iSlice, which we can pass a value, and it will slice an iterator down to that length. And it's kind of like the slice operator with lists or tuples. Count, which we just saw there, and then cycle, which is reasonably interesting. So cycle will repeat the values in the iterator passed to it. So here we can see ABC is passed into cycle, and we get the values A, B, C, and then A again at the end, and it will continue ABC, ABC, ABC for eternity, as far as I can tell. And in Python 3, some of the built-ins like zip take and return iterators rather than previously where zip returned a list. List comprehensions. I decided to choose a really big font size for these title slides, and comprehensions didn't fit on the slide, which is why I've hyphenated it like this. I think it looks okay though. So list comprehensions are a nice way to create lists from an existing iterator or iterable. And they're also what made me fall in love with Python. I mean, I'd seen a lot of this stuff before, but when I saw list comprehensions, I thought, this is for me. So here we're generating a new list. So imagine we have some people that we pulled out of a database with a Django ORM or something similar like that. And we just want to get the people's names. So we're going to call p.name for every p in people. And we get the names Ro, John, Lucy, and Tom. We can also add an if clause to a list comprehension. So here we're going to get the names of people who are not bosses. So in my house, this is me and my son Tom. And finally, with list comprehensions, we can have multiple for loops, which are sort of multiple ifs, which they're nested. So here we can see on the top line there, 2, 3, 4, 5, 6, 7. That's 1 plus 1, 1 plus 2, 1 plus 3, and so on. And the second line is 2 plus 1, 2 plus 2, 2 plus 3. And so these are all the permutations of 2 dice rolls. So generator expressions. Generator expressions look very similar to list comprehensions, but create generators. And generators are also iterators and iterable. This is where it gets a little bit confusing. So if we change the square brackets to round brackets, we get a generator object. And we don't actually get the values out until we iterate over the generator. So we can pass the generator to list. So in this case, we can actually remove the round brackets from the generator because we're just going to put them straight into list. And we can see we get the values out. So this is the same as our list comprehension. They're also useful in for loops if you don't need the intermediate list. So rather than going through all of the, rather than putting everything in a list and then iterating over the list, we can just use a generator expression like this. In likelihood, though, you would probably just have a for loop over people and then do something with pname in the loop. So generators are very similar to iterators, and they're generator expressions generate generators or create generators. So generators, they use the yield keyword, and they give us for free a dunder iter and a dunder next, as well as a nice side effect of returning to the yield or resuming at the yield the next time we call next. So here's another Fibonacci example. So the first time we call next on a new Fibonacci, we'll come down to the A, and we will get a value back. And then we can call next again, and we'll get another A, and another A, and another A. So if we remember our previous Fibonacci example, which is all of this carry on, the generator is quite a bit nicer to write. And it works the same way. So we create a Fibonacci, and we keep calling next, and we get our values 1, 1, 2, 3, 5, 8, 13, 21, I think. We have to be careful with these as well as infinite iterators. If we pass them to list, we can end up in an infinite loop, which is where we would use itertools.islice. Yield from is the other use of the yield keyword in Python, or the second of the three I'll mention, and possibly only three. So yield from allows us to delegate to a sub-iterator. So in this change in Python, or this was, yield from was added in Python 3.3, but before 3.3, this was a reasonably common pattern to see, which is, for x and x's, yield x. And this is fine, but in Python 3.3, we can do this yield from, which is maybe slightly nicer. That's all there is to yield from, really. So we've seen a bunch of ways to iterate, create iterables, iterators, generators. And coroutines are somewhat related, but they're a little bit off on a tangent. And they also use the yield keyword, which is why I've kind of included them here as well. And they're useful for creating pipelines of operations. And the way that we do it is that we move the yield to the right, that's my right and that's your right, the right hand of the assignment. And this allows us to send values into the coroutine. So previously we were yielding values out of a generator. Now we're sending values into a generator. So we can see yield here on the right-hand side of the item equals assignment. And we're going to be able to send values in here. So the advantage of being last thing on a Friday is that I can add these things I've learned this week, like f-strings, to my slides at 2 in the morning. Well, 2 this morning, actually. So I decided to add them here. So the way we use this, we call next to do what's called priming the coroutine. So this just advances us to the first yield, and then controls return back to where we are, and then we can start sending values in. So we're going to send in row Lucy Tom, and our printer is going to add the value 0, 1, 2 to the front of our strings. So here we send row, and we get 0 row, and on we go. And this is the best I could think of for how to sort of visually represent a coroutine. And we're going to call this kind of coroutine a sink. And we mentioned pipelines, and we'll see how this sort of works shortly. So a slightly different version here where we can pass in a predicate function. So this will print any item where the predicate on that thing is true. So the easiest way to understand what's going on here is we're going to create a predicate where we're going to check if the second letter is U. And it's only this because of my examples. So we can see that Roe doesn't pass, so her name isn't printed. Lucy does pass, so her name is printed. And then again, Tom doesn't pass, so he's not printed either. The problem with this, though, is that we've sort of tied up our filtering logic and our printing logic. So once again, filter printer is also a sink. And these are useful, but not super useful. So we'll skip over this because this is a little bit wild, but basically what we're doing, we're not going to skip over this. So here we're going to pass the sink into this coroutine. And then every time we send a value into this coroutine, we're going to send it onto the sink. So you can see this is sort of becoming more of a pipe and less of a sink. And I've added this coroutine decorator at the top here. Here it is defined. But basically what we're doing is we're just sort of automatically priming it with that call to next, and then we return the primed coroutine. There are reasons that you don't necessarily want to do this if you've got a lot of setup at the start of your coroutine. But for the rest of the slides, this is a kind of useful thing to have, and it removes some of the boilerplate that we'll see shortly. There is also a coroutine decorator in the async IO module, but that's different to this, and it does different things. So our filter that we've just seen is now a pipe rather than a sink. So there are now two arrows, one on either side. And how we use it is we can create a printer sink at the top there. We have this filter pipe, which our predicate is to print people who can drive, and we pass our printer into taxi drivers there. And then for P and people, we're going to send all the people to our taxi driver's filter pipe, which will then send them onto our printer pipe. So we can see here the two people that can drive are Ro and John. So my wife and I can drive. So this is slightly more useful. We can maybe start to see how this might become useful. And it looks like this. So we now have a small pipeline. So we can send values in on the left-hand side there, and they come through the filter and then maybe come through the pipe, through the printer at the end. And we could start to build up some quite interesting pipelines. So the Unix utility T is the namesake of this coroutine. So we're going to pass in a list of sinks, and we're just going to fan out. Sorry, we're going to fan out our anything that's sent to T to all of our sink coroutines that get passed in. So the way that this might work is we could create a log, which is our printer. We're going to have a boss filter and a driver filter, which both send to log, and then we're going to create a T coroutine, which takes both boss and drive. We'll send our people in again, and we can see here that Ro prints twice because she's both a boss and a driver, so she comes through both filters. John comes through the driver filter, and Lucy comes through the boss filter. Why you would ever use this, I'm not entirely sure, but it's sort of fun to think about and to write. And here's a visual representation of this. So values coming in on the left, getting sent to both boss and driver, and then potentially coming back down to printer at the end. So now for something a bit which you shouldn't do. So our coroutine pipelines, even when they're fairly simple, tend to look a bit like this. And the thing at the end is always deeply nested. And we know from PEP 20 that flat is better than nested. Other languages, including Bash and Elixir and Clojure, have nice constructs for dealing with this sort of thing, where we can pipe things together. So here's a whole bunch of magic. We're going to wrap our coroutines in a partial. Then we're going to wrap the partial in this powerful combinator object, which overloads the POW operator. And this could certainly be tidied up a bit. There's a lot of kind of weird stuff. This is not easy to follow, and this is also not getting a thumbs up on code review. But it allows us to do this. And as weird as this looks, this does work. So an example here, we have this range, which is not the actual range. It's one I had to define myself, which will generate the values 10 to 15. So 10, 11, 12, 13, 14. We're going to filter out only the even values to get 10, 12, and 14, and then we're going to send those onto the printer. And it works, but yeah, don't do this. So that's pretty much all I have. So we've had a look at loops, recursion, iter-tools, comprehensions, generators, coroutines, and then that stuff at the end that you shouldn't do. But thanks very much for coming and for listening. Again, that's my Twitter name, and the slides should be on Twitter very soon. I just want to thank you, and are there any questions?
Thank you very much, John. Questions?
Thanks for the talk. I noticed you had a nested list comprehension in there, but there wasn't a yellow sticky note on it saying you shouldn't do that, or it wouldn't pass code review. Is that something that you think should pass code review, or is it something that should be kind of split out into maybe a loop and a list comprehension?
Okay, so the question is, I guess, how complicated should list comprehensions be? And my kind of rule for thumb is if you're doing more than two things, don't do it. Unwrap it into a for loop. So if you are, creating a tuple on the left-hand side from keys and values, maybe, or you are, you have a for with an if, which is preferred to the sort of functional filter now, or you're doing anything slightly more complicated, or if you have to write it over 2 lines, I would suggest unwrapping it into a for loop and then just appending to a list or something like that.
I've got one further question, if that's okay. So the method you've shown of kind of composing these pipes with sinks and things like that seems quite a powerful way of transforming data with these reusable components. But you don't tend to see this style of programming very often. And I wondered why you think that might be, or even maybe this isn't Pythonic in some way.
That's quite possible. So the question is, why do we not see coroutines and pipelines more often? I think it's just weird. I don't think you can do it a lot more easily, a lot more, it's a lot easier to understand in other ways. I think the first talk I saw on coroutines, someone asked, the first question was, what was the original problem you were trying to solve by writing this code? And there wasn't really an answer. So don't do it, I guess.
Any other questions? Hi. Could you bring up the slide with the dunder power again, and maybe talk a bit why you recommended not to use that?
So why not use this?
Yeah, what was bad about that?
There's too much going on. I don't necessarily suggest you write this style of code anyway. But there are partials, there are nested functions, there are star args, star quarks. There's overloading built-in methods just to do a little trick, which is the star to create the pipeline. Yeah, you can do this stuff. It doesn't mean you should do this stuff.
Okay, so the same would be for Dunder-Mole or matrix multiplication. It's just the whole idea of chaining them is a bit complex, is that what you're saying?
Yeah, I think so.
Any more questions? I have a question myself. I find myself sometimes wondering if I should use a lambda, a partial, or a local definition of a function. Do you have a preference for that?
It depends. I've seen good uses of all three. I don't know that there's a good answer to that. I think it depends what looks good, what the rest of the style in the code base looks like. If lambdas are generally avoided, generally avoid them. I think partial is reasonably unknown because it lives in func-tools, which is reasonably unknown. So I would probably avoid that. A lot of people would probably need to look up the docs on that. So yeah, again, it depends.
Okay, thanks. Okay, that's it then, I think. So please give him a big applause.